Welcome back. In today's lecture, I am going to talk about linear tracking problems. In the previous class, what we have found that if we have to maintain a state closer to the equilibrium point or origin, then how to design optimal control. And for that, we have taken the very special class of system, that is linear time varying system, and what we found that same kind of result is equally valid if we are taking that linear time invariant system. In today's lecture, what I am going to do, I am going to extend the regulator problem into more general class of problem, that is called tracking problems. And in this class of problem, again my system is linear time varying, and we have to maintain our state close to desired point, and desired point may be anything. And since we are telling that desired point might be anything, so you can also take desired point as a origin. Still, whatever result I am going to discuss in today's class, that is valid. So let us first recap the problem of previous class, and after that we are going to design the optimal control for tracking problem. And again, formulation of problem is exactly remains the same. We have system that is governed by linear time varying differential equation. We have given performance measure, our control as well as the permissible state trajectory is unbounded, and then we have to solve the optimal control problem. And we are going to again travel with same route. We are going to define the Hamiltonian, we are going to define the state equation and co-state equation. After that, we are going to formulate one algebraic equation. Using that algebraic equation, we can calculate the control, and after that we will define the boundary condition. So same way, roadmap remains the same. So first I am going to recap. So in previous class we have taken this system, and our system is basically linear time varying system. And yeah, this is linear time varying system, and what we have assumed that xt that belongs to Rn, ut that belongs to Rn. So ut that belongs to Rn, and we have defined performance measure like this. Here this is this h as a some kind of constant, positive symmetric semi-definite matrix. So positive symmetric semi-definite matrix we are assuming. So H equal to H transpose we are also writing like this, and we are using this kind of notion. And here QT matrix, so for all T, this is again positive symmetric semi-definite matrix. So again QT transpose equal to QT, and that should be greater than equal to 0 for all T. So whatever things I am telling, that is valid for all T, all possible T, this kind of relation is valid. And similar kind of situation if we are going to consider the RT. So RT is again positive symmetric definite matrix. Here, since RT is associated with control action, due to that reason I am going to assume that this is not semi-definite, because we are assuming that control is present everywhere, and due to that reason this is positive and symmetric definite matrix, so greater than 0. So this is the notion, and after that we have already seen that in previous class it is desired to maintain the state vector close to the origin. So I have two different kind of formulation, please do not confuse. In one class of problem we have to maintain our state exactly at the origin. So if that kind of situation we have, at that time this particular part is not present, and if I have to maintain close to the origin, at that time this part also comes into picture. And what is our assumption? I do not want to use excessive amount of control, so our control expenditure is also some kind of optimal. So that kind of things we have to take care. And what we found that by defining Hamiltonian, by defining proper set and coset equation, and after that we have defined boundary condition, then we basically get one set of LTV, linear time varying equation, in terms of the state and whatever Lagrangian multiplier PT we have defined. And if I will solve that equation, either you can go via the state transition matrix or you can take help of Riccati equation, then we are able to find this particular control action. And what we found that this particular control action is somehow time varying in nature, because ft is time varying. So in this way, by solving Riccati equation, basically we are getting the kt, and we already know that what is value of R inverse from the definition of performance measure bt transpose, that is from the system. And after that, in this way I can able to design the optimal control. And let us try to see now objective of the today's lecture. In today's lecture, now I am going to generalize the result obtained for linear regulator problem to the tracking problem. Tracking problem means, suppose I have to track some kind of function or some kind of reference system. So reference system might be, in some case that might be constant, in some other case that might be time varying also. So based on our specification, suppose this is rt and t, and if you have some kind of initial condition, then you have to track this, or you have to track this kind of problem statement we have. And what we found in the regulator problem, we have to steer very close to the equilibrium point, and at that time my reference signal is nothing but 0 0. So basically this tracking problem is just generalization of the regulator problem, and due to that reason we have written these kind of sentences. And now again, our aim, I have two different aim. In first aim, it might possible I have to exactly force our trajectory by designing optimal control to maintain that state exactly, or we have to another really a little bit relaxed way, that by designing some kind of proper control action, we want to maintain our system state in the close vicinity of the reference point. So both classes of problem is called basically a tracking problem. Now let us try to see how to solve this class of problem. Again, I am going to take same classes of system. So this is nothing but LTV system, linear time varying system, and this linear time varying system is basically again containing that whatever matrix, this AT matrix, that is time varying. So each entry of AT matrix is time dependent. Similarly, this matrix whatever BT, their each and every entry is again time dependent. And what we are assuming that again xt belongs to Rn and ut belongs to Rm. And if this matrix AT is constant and BT is constant, then we are telling that system as a linear time invariant system. So whatever formulation we are going to talk, that is equally valid, and formulation become little more simple, calculation become little more simple. And due to that reason, most of time people are just discussing about the linear time varying system, because whatever result you can develop for linear time varying system, that is equally valid for linear time invariant system. So let us try to see that how to solve this class of problem. Again, whatever our performance measure, that is in that performance measure, now I have little bit correction. And what is correction? You try to see here that in this particular performance measure I am going to incorporate something, and here I am going to incorporate the boundary condition. So by incorporating the boundary condition, what happens that we are able to define the whenever we are at the terminal stage. So terminal stage means this is my, when we are at the time tf, we are our aim to maintain rtf. And due to that reason, you can see that whatever end point tf, that is xtf. So I am telling that using this I am able to steer my trajectory to close vicinity of rtf. And due to that reason, now somehow I am defining everything in terms of error. So initially, if you see the regulator problem, at that time I can define error et, that is nothing but exactly equal to xt. So etf is equal to xtf. Now my error is nothing but rt. So in place of state, if you substitute error, then formulation remains the same. So same kind of things I have done. If you remember that here I have just taken xt transpose qt and xt in the previous class. In today's class I am just going to substitute error here, and if reference is 0, then you can see that performance measure remains the same. So due to that reason, most of time if you understood the regulator problem, then tracking problem is almost straightforward. And due to that reason, some literature is also not going to talk about this class of problem. And here in the short form, I can also able to define the performance measure like this. So meaning of this symbol from here to here, that xtf rtf transpose hxtf rtf. Again I am going to assume that h is positive symmetric semi-definite matrix, and I am assuming that this is terminal cost, so that is constant, and qt, that is again positive symmetric semi-definite matrix, and rt is positive symmetric definite matrix because that is associated with the control action. So same kind of assumption remains the same. And after that, I have already told you that now instead of 0 origin, I have to track some kind of general trajectory, and that particular general trajectory is nothing but rt. And assumption is again remains the same, that final time tf is fixed, xtf is free. Why we are telling xtf is free? Because sometimes it is confusing. You can see that what I am telling, that I want to steer my trajectory towards some desired output. So people might think that desired output is known to me. Why still we are telling that xtf is free? Basically, in this class of problem, we are assuming that I have to define some kind of optimal control problem or optimal control such that I can go to the close vicinity of that particular tracking signal or reference signal. So close vicinity, there is no definition, no proper definition of close vicinity, and due to that reason we are telling that tf is even tf is fixed, xtf is free. So with that convention I am going to design or going to search for the optimal control for the linear time varying system. And again, I have already stated about this, that H and Q are real, means each and every entry of the H and Q matrix are real, symmetric, positive semi-definite matrix, and R is real, symmetric, and positive definite matrix. It means that control is going to present every time in the performance measure. And after that, now you can see that formulation is 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 remains same like the previous one. I have to define the Hamiltonian, and Hamiltonian function, again whenever we are defining Hamiltonian function, now I hope that you become mature enough that whatever quantity inside the integral I am going to take that, and these two quantity, that half xt rt square qt, and now you are already well aware about this particular symbol, and this quantity I have to take from the integral, and after that I have to define some kind of constant, or you can see that Lagrange multiplier, and dimension of this is same like dimension of the state. So xt belongs to Rn, so pt, some kind of independent time varying quantity I am going to select, that also belongs to Rn. So I am assuming that pt is nothing but p1t to p2t up to pnt. So similar kind of things I have, and this either you can tell Lagrange multiplier or some kind of time varying constant, that doesn't matter for the analysis. So I have to multiply the dynamics, and what is our dynamics? X dot t equal to atxt plus but. It means that my system is constrained to follow that dynamics throughout the state space for any value of control, any value of desired control. Due to that reason, I have to multiply pt with that dynamics, and you can see that due to that reason, pt transpose, if you take common from here, then you are able to see that atxt plus btut, that basically come into picture, and due to that reason, now this is our Hamiltonian. And once I define the Hamiltonian, then you already well aware that state equation. So everywhere inside state equation we have to substitute the optimal trajectory x star t and optimal control u star t, and due to that reason we are not talking about the state equation most of the time. We have to just derive the co-state equation. You can able to derive x dot x, if you go via this formulation, if you just solve this equation, x dot star t equal to dou h by dou p. So basically you are able to get this kind of equation, at into x star, and after that you can get bu and u star into t, and here this is time varying, so bt into ut. So most of time, due to that reason, we are not writing this kind of state equation, because we already know that our system is constrained to follow this equation. And after that co-state equation, in order to derive the co-state equation, I have to take partial derivative of Hamiltonian function with respect to x, and after that I have to put the negative sign, and if you solve this, then you can able to get this. So please be careful that h here, h is function of xt minus rt, and I am going to take partial derivative with respect to x. So basically 2 and 2 is going to cancel out, and after that xt minus rt into qt, that comes into picture. So what I have done here, that in this particular formulation, one time I have collected minus qt into xt because negative sign is there, and after that this. So if you collect these two terms, then that term basically comes into picture, and after that I have to take the partial derivative of h with respect to x. So another term that is containing x, that is nothing but, again please verify this, so this term pt transpose at into xt, and I am taking the partial derivative with respect to xt, and in order to match the dimension we are basically adjusting, because we are knowing that qt, pt and h all are symmetric. So whenever you have to do adjustment based on dimension, you know the dimension of pt. Due to that reason, dimension of pt dot is exactly same like pt, and based on that you can do the adjustment. Now third stage, I have to define the control. And how to define the control, optimal control? For that I have to solve the algebraic relation. And how to solve that? You have to take partial derivative of Hamiltonian function with respect to u. And if you do that, then you will get this value of optimal control. And now our problem is almost solved, just because I know what is my R inverse T, I know what is my BT. R inverse T I can take from the performance measure, B transpose T I can take from the system equation. Just now I have to define PT. So I have all other formulation, just I have to do in order to find this variable P star T. So if I am able to identify this variable P star T, then I am able to design the optimal control. So let us now try to focus that how to basically come up with the explicit equation of P star T. So what I am going to do, I am going to substitute this algebraic formulation, because using algebraic formulation I am able to know that what is value of optimal control. So what I am going to do, I am going to substitute that value of optimal control, and once you will substitute, then I have now equation like this. One more thing you can check here, that whenever we are solving the regulator problem, at that time this particular term, means second term, is not available. So from here it is pretty obvious that if RT, reference signal, is actually I have to track origin, at that time this term becomes 0, and addition of any matrix with 0 matrix, that is again remains the same. So in that way also you are able to verify that if you have some kind of calculation mistake or not. And if you see carefully, then this equation is linear time varying. Again this matrix is depending on time, explicitly depending on time, and you can interpret this quantity, extra quantity, as some kind of forcing function. So basically now I have some kind of virtual system, and I have started xt belongs to Rn. So in order to find pt, p star t, I have to solve equation, and order of equation now you can see that that is 2n, n for this and n for this, and this you can assume that I have some kind of virtual forcing function. So just you have to solve some kind of linear time varying non-homogeneous. Due to that equation, that term, this is non-homogeneous. If you remember the regulator problem, at that time this term is not present. So due to that reason, equation is homogeneous. Now equation is non-homogeneous, and I have already told you in the previous class also, same in this class also I am going to repeat. If you are not comfortable how to solve linear time varying equation, then I have already recorded lecture. If you see modern control theory, course code is EE-313. So that kind of actually formulation is already available on my YouTube channel. So from there you can take and see that whenever you have time varying system, then how to find the solution. So I am telling that solution, and in order to find the solution I have to define the state transition matrix. So I am assuming that a state transition matrix is known to me, and in form of a state transition matrix this is the solution. And after that what I am going to do, here you can see that xt and pt, then I have some kind of partition. And what kind of partition I am assuming that phi is phi 11, phi 12, phi 21, and 5 to 2. This kind of things I am assuming that I can able to do partition, and all terms are basically explicitly depending on the time, and this belongs to R2n cross 2n matrix. So, and this is 2n matrix. So similar kind of factorization here. So I am assuming that after factorization, now I am not going to calculate the factorization, and after that this term is f1t and f2t, this whole term after manipulation. So once you solve problem, then you are able to understand this fact, and in that way I am able to get this kind of things. Now what I am going to do here, 2n cross 1, so either you can write 1 or not write 1, that doesn't matter. After that, now you can see that I am able to write equation like this. I am assuming that a state transition matrix is known to me. I know how to solve linear time varying equation. Then I can explicitly able to solve xt star tf and p star tf. Now I have to find the boundary condition, because whenever we are solving optimal control problem, then I have a state equation, co-state equation, after that third thing that is algebraic equation, and final thing that is boundary condition. And here you can see that I am assuming that tf is fixed. So due to that reason, variation with respect to in tf equal to 0, but xtf I have to just maintain something in the close vicinity. That is our statement of problem. So I have to maintain something that is very close to this, and due to that reason, suppose this is t and this is rt, and due to that reason, what I am telling, that whatever final quantity that is not exactly known to me, or final error you can tell, etf, that is not known to me, and due to that reason, variation with respect to etf, that is not 0, and due to that reason this kind of boundary condition comes into picture. So we have several times I have discussed, and h is nothing but here error, xtf final error, rtf square, and h is positive symmetric definite positive symmetric semi definite matrix. And here at tf, you can see that I have this kind of expression, P star TF H star TF minus H RTF, by solving this equation, this particular boundary condition equation. Now what I have to do, once I know the relation between XTF and P star TF, then I am going to substitute these two quantity from the above equation, because in above equation I know the expression of xtf and p star tf. So same kind of quantity I am going to substitute here, and once you will substitute, then basically you will get this kind of expression. And now from here you are able to solve p star, because in order to find optimal control, just I have to somehow, using some proper way, I have to solve the p star, and once you will get the p star, so please check this calculation. So now everything is just a calculation, and now you can see that in the regulator problem I have just this term, and if you remember, then I have defined this term as a ft into x star t. Now I have some kind of extra quantity, that is xt. So from here, by proper grouping, you are able to understand what is kt and what is xt. So that kind of things I haven't properly written, just you can see the expression, and whatever this quantity you can see that is multiplied with x star. So x star t and remaining quantity is kt, and whatever other quantity, if you see that this quantity from here to here, that is xt. Now I can able to write the optimal control law. So our optimal control law, what is optimal control law? U equal to R inverse T B transpose T into P star T. If you see, if you solve the algebraic equation dou H by dou U equal to 0, then we found that control is nothing from here to here, and here remaining term I have, that term is nothing but P star, and now I have calculated P star. So just you have to substitute that, and after that we will get the optimal control. So optimal control for regulator problem is this. Now tracking problem, I have some kind of extra quantity Vt, and you from here you can see that Vt is nothing but this particular part, and so Vt is command signal, so modified command signal you can tell. Now if you see this same kind of things using the block diagram. So this is the block diagram of the optimal tracking problem. So I suppose I have to track RT. So this is my reference signal, and I am telling that this is my reference signal. I have to track. Then what I am going to do, I am going to define some kind of integrator, and I am assuming that all state information is available to me. Obviously, by designing the proper observer based control, it is possible to show that one can relax this assumption, but for time being you can assume that all states are available at the output. And after that I have this system. Now ft matrix, because I have to ft into xt and multiply by vt, so vt part, and vt part is properly modified by this st. Inside st we have rt, so please check it. And due to that reason I have drawn this kind of block diagram, and after that passed through bt. So this part is controller, optimal controller, and after that I have plant. So this is just the block diagram. And in previous class we have seen that there are two different approach to find the expression of P star T. One approach, you can follow the state transition matrix. Another approach that is equally valid or more elegant now, because we have several tools to solve that kind of equation, that is called Riccati equation. So in terms of Riccati equation also you are able to express P star T. So how to do that? What I am going to do, again I am going to start with this expression kt into x star t. I am going to take the derivative, and once you will take derivative, then this kind of term I have, and after that now I am going to substitute p star t and x star t. So in this particular method there is no need to worry about the state transition matrix. Now what I have to make sure that for all x, this particular matrix differential equation should be satisfied. So since this is satisfied for all xt and rt, and due to that reason you can see that if that is satisfied for all xt, then I can, and this equal to 0, due to that reason I can equate this quantity equal to 0 and this whole quantity equal to 0. So if these two quantity means bracketed quantity equal to 0, then I can tell that, I can give guarantee that this particular equality equal to 0 is satisfied for all x star t and rt. And due to that reason now I have two equations. So one is Riccati equation, and during regulator problem you might have seen this equation. Now apart from this I have some kind of extra equation, again some kind of matrix equation I have to solve. And boundary condition, after that, somehow since my kt and xt both are time varying quantity, so somehow I know that when I am going to start, now I have to know that when I have to stop. And for stopping, at the stopping time, what is value of kt and xt we have to know, and that kind of information one can gather using the boundary condition. So if you see the expression of boundary condition, that is p star tf, that is h x star tf minus h rtf. And after that now you are already well aware that once I will converge in the close vicinity of the tracking point, at that time ktf equal to h, and xtf similarly from this expression I can able to write that is nothing but minus h r tf. And why we are telling that? Because for all time I have to make sure that this equation, this boundary condition is satisfied. Due to that reason at terminal point also this equation should be satisfied, and due to that reason I come up with these two algebraic relation, and using this algebraic equation I can able to solve P star. So final aim, just you have to solve the P star, because you know by solving algebraic equation that what is optimal control, that is minus R inverse T, that is coming from performance measure, B transpose T, that is coming from the system, and that is input matrix, and after that P star T I have to find. So P star T you can able to find using either by state transition matrix by solving time varying differential equation, or you can able to apply the approach of Descartes equation. So both approach is equally good. And now I am going to illustrate the today's formulation by taking some example, and I have already told you that whatever result you have developed for time linear time varying system, same kind of result is equally valid for linear time invariant system. Just you have to replace AT and BT matrix by some kind of real valued constant matrix. So each entry of matrix is some kind of real numbers, just a real number. Suppose I have to minimize this performance measure. So from performance measure also you are able to guess what is your tracking point. So you can see that tracking point is nothing but at time t that is specified to me, I have to maintain in the close vicinity of 1. So by seeing performance measure, you are able to understand this. If this is not present, then you have to maintain in close vicinity of 0. Now, the final time t is specified, xtf is free, and I am assuming that in this whole section, I am going to assume this, that admissible state and control are not bounded. So obviously, in the next part of this lecture, I am going to talk how to design optimal control if admissible state and control both are bounded. Now, what is our objective in this problem? That optimal control law I have to find, and I have already told you that by seeing the performance measure, I am able to understand that where I have to maintain my final trajectory. And in this particular performance measure, you can see that I have some specification about the x1, but there is no specification about the x2. But this is second order system. It means that x2 might be anything. I do not worry about the x2. Just I have to make sure that x1 t at the final time t, that is very close to 1. And due to that reason, I have flexibility on the x2. And if I have flexibility, then I can, without loss of generality, I am going to assume that as a 0. So now I know the A, I know the B. So from this equation, you can see you are able to express A and B by seeing this equation. So I can also write X as a x1, x2. And once you write like this, then A matrix is nothing but 0, 1, x2. So R1 into C1, and after that 2 and minus 1. So if you multiply A into X, so R1 into C1, then X2 comes into picture here, and R2 into C1, then 2x1 and x2 comes into picture. And after that B, you can see that ut that belongs to R, so I have B equal to 0 into 1. And here whatever quantity that is multiplied with here, that I am defining as a H, here that as a QT, and here I am defining as a R. So same kind of nomenclature I am going to use here. So Q is 200 H. So please check the performance measure. R is this, and RT we know already because I have a specification about x1, but no specification about the other one. So same kind of things basically I have written here, just in order to maintain consistency. And after that, I have told you that I have two different way. So one of the easier way, because nowadays we have several software tool to solve Descartes equation, and due to that reason, what you can do, if I have simple problem, so here you can see that kt is actually k11, k12, and this is symmetric matrix, so k12, so this is k12 and k22, and due to that reason, instead of I have 1, 2, 3, 4 equations. I have just 3 equations. If you assume that kt equal to kt transpose t for all t, that is symmetric matrix. So I have 3 equations, and after that I can also able to derive the equation in terms of x1 and x2, and after that in using solving this equation and putting boundary condition like these two, I am able to get the optimal control and optimal control. So please check it that this is the optimal control or not. Similarly, suppose if I have system like this and I have to track some kind of time varying signal. Here everything system remains the same, everything remains the same. Just I have change the performance measure, and I am assuming that whatever quantity I have to track, that is exactly I have to track, and due to that reason first term is not present. Now you can see that my tracking desired tracking output is 0.2 t, that kind of things, and I have to define the optimal control. So again you can go in the same way, again you can solve the Riccati equation, and by solving it you are able to define the optimal control by incorporating the boundary condition, because whenever you are solving the equation at that time you need the boundary condition. So now it is time to conclude the today's lecture. So in today's lecture, basically I have talked the generalization of regulator problem, that is called the tracking problem. What we have observed that formulation is exactly almost remains the same. And one more thing that I haven't discussed till now, that how to simulate. So simulation part we will do in the later part of this course. So with this remark, I'm going to close the today's lecture. So thank you very much.